we defined what vectors are, we're going to start doing stuff with them. And there are two very exciting things that we can do with vectors. One is that we can add them. Okay. I want to just point out that I've titled this Adding Vectors in Vn. In order to add two vectors together, they have to be in the same space. So if I have two vectors in 2 space, I can add them together and I'm going to get another vector in 2 space. If I have two vectors in 3 space, I can add them together. If I have a vector in 2 space and a vector in 3 space, I cannot add them together. They are not the same type of object. So standard rule in math, when you're adding, you can only combine like terms. Vectors are not like terms if they live in different spaces. Okay, so that's very, very important. Okay, I'm going to start by just working in 2 space, just because I have a nice copy of 2 space here in this whiteboard. Okay, let's suppose that I have in 2 space a vector v and a vector w. Okay. So I've drawn them in here, and I would like to try to calculate what v plus w is going to look like. Okay. Well, there's a nice geometric way that I can do that. Okay. What I'm going to do is I'm basically going to think of this as this vector tells me to go this distance in this direction. Vector w tells me to go this distance in that direction. So both of them are sort of giving me some directions. Go this far in that direction, go that far in that direction. Okay. If I'm adding the vectors, I'm just going to follow both sets of directions. So if I'm looking at v plus w, what I'm going to do is I'm going to say, okay, let's suppose that I start my journey here. I'm going to do v first. I'm going to follow its directions. So I'm going to go this far in this direction. Once I've done that, now I'm here. Okay. There's nothing in the directions that says turn around and go back to your starting point before you do what w tells you to do. So from here, I'm going to follow the directions for w. So I'm going to go this far in that direction. To accomplish that, I'm just going to translate w. Let's see, let's make that the same length. I'm just going to translate w so that the tail of w is at the tip of v. Once I've done that, now this is the vector v plus w. That's the vector that takes me from my initial starting point to my final ending point. First doing what v says, then doing what w says to do. Okay, kind of cool. This is sometimes referred to as the parallelogram law, because you'll notice if I were to draw v in translated position up here, I've essentially created a parallelogram here with 2 copies of v as sides and 2 copies of w as sides, and this diagonal is the vector sum v plus w. I don't ever find it necessary to draw in the full parallelogram, because to add them, I'm just going to translate w, put its tail at the tip of v, and add them. Now, I've illustrated this in sort of a 2-dimensional space, but the same thing holds in 3 space. So let's suppose I'm in 3 space, and I have this vector, which I'm going to call v, okay, and then I have this vector, which I'm going to call w, okay. And right now I've got them so that their tails are at the same location. Well, if I wanted to do v plus w, I would simply take w, translate it so that its tail was at the tip of v, and then v plus w would be the vector that points from the tail of v to this tip of the translated version of w. Okay. So the same principle holds. And I can actually illustrate that fairly nicely. Notice, if I've got v and w here, and I put them with their tails together, okay, I could, right now they don't really fit on the whiteboard because of the way they're pointing. But if I just sort of rotate things a little bit, I can fit them there. And so I could draw a picture and say, okay, there was v, and there was w, and this is representing that vector sum in 3 space. I just didn't draw things with the coordinate axes. So the directions are a little bit warped here, because what I've done is I've just sort of said, okay, I'm going to just rotate everything and put it down. But if I just want to illustrate the sum of two vectors, those two vectors I can always draw on some plane. So I can just make that plane my whiteboard or my piece of paper. So an illustration like this. Now I want to be careful. If I wanted to actually draw this with accurate directions, that's a much harder task. But if I just want to illustrate what's happening when I add two vectors, I'm just putting them tail to tip in order to add them. Okay. Now, very often, particularly when we are in 3 space, we're going to choose to do things algebraically rather than drawing lots of pictures, particularly as we start working with more than just 2 vectors. Because if I have a third vector and it doesn't lie in the same plane as the first 2, then I'm not going to be able to fit it neatly by just rotating things to put things onto the whiteboard. All right, so let's suppose in 2 space, I have the vector. I'm going to work in 2 space just because it's easier to illustrate, but this will generalize to 3 space. Let's suppose I have the vector -1, 2, and W is the vector 4, -3. Okay. Now, what I'm going to do is I'm going to first of all illustrate what those vectors look like and what the sum looks like, and then we'll calculate it and get the component form of it and see how the algebraic method of calculating things coincides with the geometric way. Okay, so I'm going to draw both vectors initially just in standard position. So here's V, -1, 2. Just to keep track of things, I'll let W be a different color. So 2, 3, 4, down 3. Okay, so there's my W. So if I want to calculate V plus W, I'm basically going to say, okay, let's take W and let's translate that. So I'm going to put the tail of W at the tip of V. But I'm going to preserve the same length and the same direction. So I'm still coming 4 over and 3 down. Okay. So there's my W in translated position. You'll notice it's parallel to the other W because they point in exactly the same direction. Okay. All right. Excellent. So we've got that. Now notice that means that this vector here, that's my V plus W. And how did I get there? Well, I followed the directions for V, which told me to go 1 to the left and 2 up. Right? That's what V told me to do. And then I followed the directions for W, which told me to go 4 to the right and 3 down. And I basically followed them in this direction. I did this pair first and then this pair. But notice, if I just look here, this is what I did horizontally. I went 1 to the left and 4 to the right. That's a net change of 3 to the right. And it does look like we end up having come 3 units to the right. Because notice V plus W here is drawn in standard position. Okay. If I look at what I did vertically, I went up 2 and then down 3. Well, that's a net change of going down 1. If I simply add the components, -1 plus 4, 2 plus a -3, I'm going to get 3, -1. Going 1 left and 4 right is equivalent to going 3 right. Going 2 up and 3 down is equivalent to going 1 down. So we say that we can add our vectors component-wise. Okay. I'm going to just write that out sort of generically in 3 space. Okay. So let's let V be V1, V2, V3. be a vector in 3 space. Notice what I've done here is I gave the vector a nickname, but then I used variables for the individual components as well. You'll notice there are no bars over them. These are numbers. These would be in the role of the -1 and the 2 and the 4 and the -3 that we had here for these vectors in 2 space. There are 3 of them because this is a vector in 3 space. Okay. I could, if I wanted to, call these guys x, y, and z, but I kind of prefer to just use those subscripts because now I'm going to introduce another vector, w, and I can let its components be w1, w2, w3. That's also going to be a vector in 3 space. The rule for how we add vectors is that v plus w is v1 plus w1, v2 plus w2, v3 plus w3. So we simply add component-wise. We combine the like components. All right, excellent. And I think it's important to be able to visualize what's going on, so to use that geometric interpretation of things, but it's also important to be able to do the calculations, and very often we're going to rely on the algebraic definition of addition in order to accomplish things, but very often we're going to want to be able to draw a picture of what's going on as well. One time where I might be adding vectors is if I'm applying 2 forces. Okay. If F1 is force 1 and F2 is force 2, and let's say I'm applying both forces to the same object. Okay. So maybe I'm pushing on the object this way and somebody else is pushing on the object that way. Okay. Well, what's going to happen if I apply both of those forces? The object's going to move that way. Okay. Adding these 2 forces, if I write F1 plus F2, if I just call that sum F, this is what we would call the resultant force. So when multiple forces are applied to the same object, we add those forces together, and it's as if we were just applying that one, what we call the resultant force, to that object. It's a very useful application in physics.